Welcome to this talk about the Measure-and-Reprogram technique 2.0, multi-round Fiat-Shamir and more. My name is Jelle and this is joint work with Serge, Fehr and Majenz. Our work is about proving Fiat-Shamir digital signatures and in general Fiat-Shamir zero-knowledge proof systems secure against quantum attackers. Where by secure we mean secure in the quantum random oracle model. What we do is we extend an existing QROM technique to a larger class of applications, notably multi-round Fiat-Shamir signatures, of which MQDSS is an example, bullet proofs and sequential OR-proofs. And finally, we also show that the reductions that we get from applying these techniques are essentially tight. I'll dive right in by explaining the quantum random oracle model. Suppose we have some protocol that makes use of a public hash function. Then proving security in the QROM means that we model the public hash function as an external random oracle to which all parties in the protocol have quantum query access. And this means that the function cannot be computed locally, but all parties can query a superposition of inputs. And this is a natural assumption since the hash function is assumed to be public. Anyone can build a quantum circuit to evaluate it. And once you have a quantum circuit to evaluate the function, then it's easy to evaluate on a superposition of inputs. But the problem is that in many classical random oracle model proofs, we want to observe the queries that the adversary makes. But as you probably know, observing a quantum state can cause it to collapse. And if the query state of the adversary collapses, this might as well collapse the internal state of the adversary, and then we can no longer predict anything about the adversary's output. In general, that is, because we present a theorem that deals with so-called multi-input reprogrammability of the QROM. It says that if we are in this situation where we have an adversary making Q quantum queries to some random oracle H, and then outputs an array, so I use the bold font here for arrays of input values to the oracle and some additional output Z, such that we know we know something about this output, the probability of this output being such that X together with the hash values of X and Z satisfy some arbitrary predicate V. Then there exists a simulator that can sort of creep in between the adversary and the oracle and choose N of the adversary's queries at random, measure them, and on the input that it finds, so in this example N is 2 and the simulator finds xi and xj. It can then reprogram the oracle to fresh random values theta I and theta j and continue the run of the adversary such that its final output x bar z bar will satisfy the same predicate v, but now with respect to these freshly programmed random values theta. And as you can see, we can even compare the probabilities for specific choices of this array x naught. But by summing the inequality, we can also make more general statements. And of course, as you can also see, this all comes at multiplicative loss of order q to the power 2n. But indeed, they are polynomially related for constant or logarithmic n. Right. Another observation that we can make is that instead of talking to a real random oracle itself, the simulator can also use a quantum secure pseudo-random function in order if A is at least computationally bounded, so that he will not notice the difference. Right, so that's the main technical result. It may all seem a bit abstract at this point, but we can actually use it and apply it to prove security of multi-round Fiat-Shamir. So very quickly, multi-round Fiat-Shamir takes some public coin interactive proof system by n and turns it into a non-interactive scheme. And we show that the advantage of the best adversary against the non-interactive scheme is at most order q to the power 2 n times as big as the best adversary against the interactive scheme. And indeed this is tight because in our paper we provide an attack. First, we provide an attack for typical 3-round schemes, the so-called sigma protocols, which indeed boosts the success of the best interactive adversary by a factor q squared, showing that for n equals 1, this loss is optimal. And then we extend the attack to a somewhat artificial multi-round scheme, and we get almost the same boost except for this factor n to the power minus 2n. But since we're usually considering n to be constant, that means that asymptotically q to the power 2n is optimal as well. Okay, for the rest of the talk, I'll give you a bit more detail about how the Fiat-Shamir transformation works, how the original result is applied to prove it's secure, and then we'll come to the motivation for this new work, namely multi-round Fiat-Shamir, and I'll discuss what we need to prove that secure. Then I'll give you the proof idea for this main result that we have, and I'll finish off by talking about yet another application in the sequential OR-proofs. Right, so suppose that we have this 3-round identification scheme where some proofer can prove its identity by sending a commitment to a verifier, and then upon receiving a challenge, this must be a uniformly random challenge, uses its knowledge of some secret key to compute a response. And then the verifier, who of course knows the public key of this prover, can compute some predicate on the messages to verify that indeed this prover must have known the secret key. Now, since this is an interactive protocol, we could ask if we could make it non-interactive, and the Fiat-Shamir transformation says that we may do so by introducing this public hash function h, and then let the prover, instead of waiting for a random challenge, compute a challenge himself simply by hashing the public key in the commitment. Then it only needs to send the commitment and the response, since the verifier on his side also knows how to evaluate h, so it can recompute this challenge and verify again that the response is correct with respect to this particular commitment and this particular challenge. Additionally, the prover could send a message along with this commitment and response, as well as include it in the hash. Including it in the hash ensures the integrity of the message, which combined with the proof of identity makes for a digital signature. So this is the idea of Fiat-Shamir signatures. Well, to prove this construction secure in the QROM, Fehr, Majenz and Schaffner in 2019 presented the Measure-and-Reprogram technique, which is basically the same as the multi-input version, which I already presented to you. Except that now the output of the adversary is just this single hash input x along with c. And the simulator now chooses just one of the adversary's queries at random, measures it, reprograms the oracle on this input to a fresh random value theta. And then we again get the guarantee that some predicate v holds now with respect to theta. Up to a q-squared loss, and also here we have an additive error term. But the theorem has the promise that even when summing over all possible instances of x0, the error term remains negligible, so we don't have to worry about it. Okay, now I'll finally show you how to apply this tool in a reduction for the plain Fiat-Shamir transformation. What we want to do in the reduction is turn a proofer against the non-interactive Fiat-Shamir scheme into a proofer for the interactive scheme to show that both are approximately equally hard to break. Well, the pattern can be matched as follows. We know that the adversary will output a public key, a commitment, and a response. So the public key and the commitment take the role of X, and the response takes the role of C. Which means that we can start up an interactive protocol by running the adversary as a subroutine and just wait until the particular query comes up that we have chosen randomly to measure. Once we've measured it, we have a public key and a commitment. So we can send that to the interactive verifier. The challenge that we get in return, we program into the oracle and feed it back to the adversary. And now we just have to wait for the adversary to finish, and we get a response, which we then forward back to the verifier. And now, of course, with this inequality at hand, we know that the probability that this response is correct with respect to this challenge, which is represented here by theta, is approximately the same up to this Q² loss as the probability that the original adversary can break the non-interactive Fiat-Shamir scheme. So that's the reduction. But as I said, this is only a plain Fiat-Shamir for 3-round schemes. The main topic of the current work is about multi-round Fiat-Shamir. And indeed, there exist many 2n+1 round public coin interactive proof systems for constant but also logarithmic n, where we can again remove the interaction in a Fiat-Shamir heuristic way. It looks like this. We have an interactive scheme consisting of many rounds. And just as before, all these uniformly random challenges can be replaced by outputs of some public hash function, which the verifier can compute on its own. So that the proofer only needs to send the n different commitments and a final response. And that's enough for the verifier to check the verification predicate. But now, of course, in the reduction, we need to extract all of these commitments, all of these hash inputs, in order to reprogram the oracle value to the challenges that we get from the interactive verifier. Now, to do that, obviously what we need is a measure-and-reprogram technique, but now one that can handle multiple measurements. Well, of course, that is exactly the theorem that I already presented to you at the beginning of this talk. But let's for a moment assume that we don't yet know how to relate the left-hand side to the right-hand side scenario. How would we go about proving this inequality starting just from the single input measure-and-reprogram tool? What we do is, starting from this multi-input adversary, we simply rewrite its output, this array consisting of x's, rewrite it as just x1 with some z prime, where now we sort of put all the other x values, x2 up to xn, inside z prime. And it also contains the original additional output c. So we really didn't do anything except just some formal trick, rewriting. But now the output has exactly the form to which we can apply the single input result. Namely, we get the existence of a simulator that picks one of A's queries at random, measures it, finds x1, and reprograms the oracle at x1 to theta1 such that now the predicate holds with respect to theta1 instead of h of x1. And note that here we made the choice to let S talk to the real random oracle instead of letting it use a pseudo-random function. And the reason for this is that we can now consider A and S together as yet another algorithm, which just has this particular output x1 c prime, which we can again rewrite such that now x2 is the prominent hash input and z double prime has all the other x's and the original z. So that, of course, as you can guess, we can apply the single input result again to now measure x2 and continuing for n times, we will eventually get an algorithm which outputs x1 up to xn and z such that the predicate v checks out with respect to theta1 up to theta n. But what is now the loss factor that we get from this inductive application? Well, from the first application we get a q-squared loss as well as this additive error term. And then in the second application we're up to q to the fourth and we have two error terms. So continuing the pattern, we indeed get this promised q to the power 2n multiplicative loss and a sum of n error terms. And if you remember, we had the promise that for each I, summing over all possible instances xi naught, this error term remains negligible. So surely summing over n of them, keeping in mind that in applications n is constant or logarithmic, the whole sum will remain negligible. But the problem is that this is not what we need. If we have a careful look at the inequality down here, we see that this is for one particular choice of the array x0, so for one choice of combinations x1 up to xn. And if we sum over all possible arrays, we're going to sum over many more values than just each of the xi's summed independently. So we can no longer control the size of this combined error that we have here. And this proved indeed to be a substantial barrier to completing the proof. So what we had to do was go back to the original single input result. And you'll now see why we call it the Measure-and-Reprogram technique 2.0. Because what we did is we improved the original single input result. We gave a different proof that doesn't have the need for this negligible error term, which makes the statement cleaner. And well, for single input applications, we get a negligible quantitative improvement. But most importantly, we lose the error terms in the multi-input case. And we get the result that we wanted. Now, one small issue that I have to mention as well, if we now want to apply this multi-input reprogramming results to multi-round Fiat-Shamir, there's one more thing that we need to take care of. As you can see, this inductive application of the single input result does not give us any guarantee on the order of the hash inputs that we extract. Here in this example, x2 is extracted before x3, but also before x1. And in the reduction that we want to perform, the interactive verifier expects these commitments in a particular order. We cannot just send it com2 first and com1 only at some later point. So somehow we need to ensure that we extract the commitments in the right order. The way to do that is simply to include the previous challenge in the hash for the next challenge. which would mean in this example that before the adversary could even query x2, it needs to know the value of θ1, since it will be a part of x2. So that enforces the adversary to query all the hash inputs in the correct order. This is not our contribution, this is folklore knowledge, also for classical multi-round Fiat-Shamir, but I just wanted to mention it to complete the analysis. Okay, so finally a few words about another application of our new technique, namely sequential OR-proofs. This is something introduced by Liu, Wei, and Wang in 2004. And it's Fiat-Shamir with a twist, which allows a prover to prove the truth of at least one of two statements, x1, x2, without revealing which one. So it's a proof of the disjunction, really. And how does it work? Well, we start from a simple 3-round Sigma protocol, and we use a hash function to turn it into a non-interactive scheme. But now the challenges are computed over cross. The prover has to provide x1, com1, x2, com2, and then uses h of com2 in order to compute the response that will be used to prove the statement, the truth of statement x1. And vice versa, it uses h of com1 to compute the response that will be verified to determine the truth of statement x2. Now, if we look carefully, we see that only for this statement corresponding to the commitment that is the first out of the two that gets queried to h, only for this statement the prover needs to actually know a witness in order to compute a valid response. Why is this so? Well, let's have a look. Suppose for now that com1 is the commitment that gets queried first. Then before having anything to do with com2, the prover already knows h of com1. In other words, knows the challenge that it will need to compute a response to. But by the honest verifier zero knowledge property, knowing the challenge before knowing the commitment allows one to compute the fake proof. So to find some com2 and response to such that this predicate is satisfied for x2, even without knowing a witness for x2. And then if com2 has been determined by this fake proof, then the prover can query it to h to find the challenge, which now using a witness for x1, it can compute a valid response, so that also the other predicate is satisfied. So the security reduction works similarly. We want to use a non-interactive adversary to convince one of the two verifiers, or the verifier on one of the two statements. But note that in order to do so, we have to extract both com1 and com2 from this non-interactive adversary. Namely, we have to extract com1 because this is the commitment that we are going to submit to the verifier. Remember, we're assuming that x1 is the statement that is actually true. So the com1 is the one that we're going to submit to the verifier. But we also need to extract com2 because com2 is the input to the random oracle on which we need to reprogram in order to inject the challenge that we get from this verifier, so that the response computed by the non-interactive adversary will be valid with respect to com1 and this challenge that we reprogrammed to. Yeah, indeed, using the multi-input measure-and-reprogram technique, we can now for the first time provide a QROM reduction for this sequential OR-proofs. That concludes the talk. Thank you for listening.